All right. Hi, everybody. Here we are in section 5.3. Um, this video from 3 Blue 1 Brown, I think I'm going to have you watch this right now. I'll communicate with Gavin and Jack. So um, hopefully you've already watched the guided notes and maybe this one too. And then we're getting into the stuff from the text now. So fundamental theorem of calculus. We've got an area function here. The area function is big F of x, so that's an antiderivative of little f. And the idea is that the derivative of an antiderivative is the original function with a change of variable kind of thing. So um, that relationship is cool. And if it was just a function that looked like this with a constant number on one of the boundaries and then a variable on the other one, using the fundamental theorem of calculus part one would just be as simple as, the derivative here just looks like this little thing. Um, but it's going to be a little bit more complicated when instead of just putting an x in the boundary, if we have some more complicated function in the boundary. Um, so the idea here being, in example 3, for part A, we're going to look at taking the derivative of an area function where that area function starts off at a fixed point A, and then it goes off the right-hand side of it is determined by the function x squared. And so let me go ahead, let's click onto this. Oh, I need to, sorry, let me open up this web browser so that when I click the GeoGebra link, it works correctly. Oh, that's fine. And this one, okay, that's fine. Boom. All right, so yay. Okay, we're up on the same thing. Here we've got the function 1 over 2 plus t mapped out. That's our green line. And the idea is instead of the right-hand boundary being governed by just a normal x, the normal x is in blue right now, and x squared is going to be in red. As we change that variable x right-hand endpoint, right now it's a half, so x is at a half and x squared is at 1/4. You're going to see that, as x changes, x squared changes as well. And the idea is, as this goes on, more areas being swept out by the one that has x squared as a boundary rather than x. This is going to keep moving faster and faster, whereas this one's going to move pretty constant. Um, and so, we could let that go out a little bit farther. But the idea is instead of having x on the boundary, we've got x squared. And so this boundary is moving faster than it otherwise would. And in this context, we are taking a derivative. We've got this d over dx derivative operator. So we will be taking a derivative. We're going to be doing the fundamental theorem of calculus, part one. But when you take the derivative of an area function and the boundary of that area function is being determined by something that isn't just plain old x, in this case it's x squared, we need to use the chain rule. This is wild, but we're taking a derivative and we need to use the chain rule because x squared is acting as the inside function and this whole integral part is acting as the outside function. Yeah, it's weird. So as we go through this, let's see if we can, do this correctly. We want to maybe, one thing that we could do is identify, maybe the big derivative will just be the function that we see inside there. But if we do f prime of g of x, then we're going to have f of g of x times g prime of x. So, gosh, yeah. So this is what we're actually going to be looking out for. And what that looks like, g of x is our little function. G of x is x squared in this case. Maybe that's what I should have written. All right, let's write this up over here, still in orange. G of x is equal to x squared. All right, so hopefully when I start writing this, it makes some sense. What we're going to do is look at our little function. The derivative of this area function ends up being the little function, or sorry, the derivative with this on the inside. So, goodness, let me just write it and then it'll make some more sense. So, instead of t, we've got x squared. That is the derivative of the area function. That's the derivative of everything that we see in this integral. But then we need to multiply times the derivative of the thing that we have in the boundary. So now we need to multiply by 2x. And so the end of this ends up being 2x over 2 plus x squared as an end result. And, I don't know if you noticed, but this has been hiding in the background the entire time. And in this one, I ended up using the fundamental theorem of calculus part 2 that we're going to see very soon. But the idea with this part is if you take the antiderivative of the inside function, which in this case, this is 1 over 2 plus t. So it's 1 over something. The antiderivative of like 1 over x is the natural log. So when you take the antiderivative of this, we get the natural log with the absolute value parts. Here we're plugging in the x squared for t. Here we're plugging in a for t. And the idea is that when you take the derivative of this antiderivative, you end up getting 2x over 2 plus x squared. Like we did down here, on this part, you end up doing a chain rule, as you take the derivative. So doing the chain rule on this part means that you got 1 over 2 plus x squared, and then times the little inside function there. But yeah, this is utilizing the fundamental theorem of calculus part 2, which is practically how we're going to evaluate integrals. But here we're using the fundamental theorem of calculus part 1, taking the derivative of an area function. So we're really just trying to get more used to this notation. I don't know that we're going to do a ton of problems like this, but let's go ahead and do a couple more and see if we can get a feel for it. In this case, we're taking the derivative of an area function, except now the function's in the bottom bound. And honestly, if this is the case, I think I would probably immediately switch this so that we just throw a negative sign on everything and we exchange those bounds. That's one of the integral properties, right? Is if you exchange the bounds, the value of the integral is the opposite. So that's what we did first. And then we're going to do the chain rule on this part. So the idea is taking this derivative, we get the area function with 3 minus 5x in the place of t. And then we multiply this times the derivative of the inside function. So the derivative of the inside function is -5 because that inside function was 5x. So, okay. Yeah, I'm sorry. I wrote a couple of negative signs there. Right. So this negative sign is the one that's coming from reversing the boundaries. So the pink one's there. And this negative sign is coming as the result of the derivative of 5x out here. Yeah. So, when we multiply those together, it would be more simply put as just e to the, well, I guess negative 5x on top, and the 3 and the minus 3 will cancel out. So it looks like that's a pretty good antiderivative there, or I guess derivative of an area function kind of thing. But again, that's the chain rule in action. In this last one, we've got variables in both boundaries. This is chaos. Um, what we can do is split this up into two integrals. And the idea being we imagine some point A that's in between the two boundaries, and we split this up integral, based on this new point A. So on the lower one, we'd be going from x squared plus 3 up to a of cosine of t dt. And then we can pick things up at a and go to 1 plus 5x of cosine t dt. So yeah, that looks wonderful, right? I mean, if we wanted to continue doing this, I'll try to do it quickly. Don't worry about this too bad. So I'm going to put a negative sign there. I'm going to put the x squared plus 3 up on top so that we have our constant boundary on bottom. Okay, and the antiderivative of cosine is just sine. So we're going to do negative sine of x squared plus 3, and then we're going to multiply by the derivative of the inside, so times 2x. And then plus sine of the boundary times the derivative of the boundary. And I think that we've accomplished the chain rule there. Yes, and we've done this. This is a challenging problem. I don't think that we are going to build on this too much, but it is important to know that this can exist. It's important to know that we can combine the fundamental theorem of calculus with the chain rule when there's some kind of wacky boundary on the outside. All right, give me a second. I need to check up on. Okay, so now we're getting on to fundamental theorem of calculus part 2. The big idea here being that we can calculate a definite integral. So we're just finding the area, between two values, a and b. Yeah, we're finding this definite integral by finding an antiderivative of the function that's in here, and then we take the difference of the antiderivative evaluated at those endpoints. So I hope you remember this from the video, that we can get the area in between 1 and 7 by evaluating the antiderivative at 7 and then subtracting off the antiderivative evaluated at 1. And we just get what's left over. And so let's go ahead and practice on these three integrals. This is great. We're doing integrals together. The antiderivative of e to the x is just e to the x. So the way that we'll notate this is we'll write the antiderivative inside these brackets, and we will copy those boundaries down, so 9 and 0. And then the idea is we evaluate our function at this top boundary, and we subtract off evaluating at the bottom boundary. So the function, this number at the end is just e to the ninth power minus 1. And that's our answer. It's great. Part B. So we calculate an antiderivative. 1 over x turns into the natural log of the absolute value of x. And then we've got 3 and 1. So then we're going to plug in 3, natural log of 3 minus the natural log of 1. I suppose in this case, having those absolute values weren't absolutely necessary because these are both positive numbers. So, natural log of 3 minus the natural log of 1 uh, is not too big a deal. The natural log, it'll just be the natural log of 3 because the natural log of 1 is 0. So that one's good. And then number C, or letter C, we're going to take the antiderivative of x to the fifth. That is 1/6 times x to the sixth power. We're undoing the power rule, so we add 1 to the exponent and divide by the exponent. And then we plug in 1 for the first part, and then we subtract off, throwing in -2. And so we would get 1/6 minus, oh my, 2 to the sixth power should be 8 times 8, which is 64. Okay, so 64 over 6. That'll turn out to be -63/6. That could be reduced, but it's fine. I guess, yeah, dividing by 3s, that's -21 over 2. Okay, that's fine. Cool. And that makes sense because, just quick checking in your head that this is a reasonable amount. X to the fifth is an odd function that goes up like this. And if we're evaluating it from -2 out here up to 1 here, we're going to have more area on the bottom than up on the top. So we are expecting a negative value out of this overall integral. So that makes sense. Cool. Example 6 looks like construct a function, little f of x, whose derivative is sine of x, and which has the value -3 at 0. So this would be very similar to what we did, I think, in section 4.7, where we were working with antiderivatives. The derivative, oh geez, of negative cosine is equal to sine. So, if we're constructing f of x, negative cosine x plus c seems like a good general antiderivative. But in this case, we want to figure out, at x equals 0, we want to set this to be equal to 3. So negative cosine of 0 plus c is equal to -3. And now we're solving for c. Cosine of 0 is 1, so we've got -1 plus c equals -3, so that c is equal to -2. Looks pretty good. Yeah. So we would have negative cosine minus 2 as our function. And that checks out. It should, it should have a value of -3 at 0. Yeah, that's good. So that was very similar to something that we've done before. All right, let's keep going. I think we've got a little bit more time. Um, Here we're looking at the definition of an indefinite integral. That is the antiderivatives that we've talked about before, so there's not too much to talk about there. Evaluate these indefinite integrals. Um, I mean, we've done most of that already. I mean, this one's just reversing the power rule. So this would become x cubed minus 2x squared plus 7x plus c. The next one would become the antiderivative of secant squared is tangent, right? Tangent t plus c. And then this one would be the natural log of the absolute value of x plus c. Okay, great. Those aren't, super exciting. Um, Doing these, I think, is a little bit more exciting. So let's use the fundamental theorem of calculus, okay? We're using the fundamental theorem of calculus part 2 here. And the idea would be, okay, we create an antiderivative, uh, x cubed minus 2x squared plus 7x, and we evaluate that at 2 and negative 3. Notice that I'm not bothering to put the plus c in this part. If I did, it would cancel out when we do the subtraction between these two. So really, all we would need to do on this one is do 2 cubed minus 2 times 2 squared plus 7 times 2, and then subtract off negative 3 cubed minus 2 times negative 3 squared plus 7 times negative 3, and continue to solve that down so that it makes some sense. But yeah, for a polynomial like this, where it's defined everywhere, using this fundamental theorem of calculus part 2 is totally reasonable. For this next one, notice, think we might be a little bit wary on this kind of a function because 1 over x will look like this. So there is a discontinuity in this function at x equals 0, but these bounds don't go through x equals 0, so we're probably still good to go. We would just be going from -5 up to -1 and calculating this kind of an area. One of the issues here, though, this is where it really does make a difference, that when we take the antiderivative, um, we use a natural log kind of thing. So let me break this out, and then we'll start writing over here. Um, the absolute value, of x inside of a natural log will make this work. So we would end up doing the absolute value of -5 inside of this part, and then subtracting off natural log of -1. There we go. And again, the natural log of 1 is just 0. So this ends up just being the natural log of 5. Um, oh, and I did that backwards. That's why it's turning out to be positive. My bad. I need to put the top boundary in first. Yikes. Okay. So my bad on that one. Um, Here we've got 0 minus the natural log of 5. So it's just the natural log of 5. This last one, let's do this. We're going from -1 to 1 of this function. Here, let's draw this again. In this case, since we're 1 over x squared, we go up like this. And we do have another discontinuity at x equals 0. And that is a problem because we're trying to integrate from, over here at -1 all the way over here to +1. And getting up in this infinity part is not good. We can't just use the fundamental theorem of calculus here because we are not continuous here. And if we go back up um, and look at the fundamental theorem of calculus part 2, little f needs to be a continuous function. And this one is not. Okay, so I think that's where we're going to end things today. Thank you for working through this. Next time, we're going to be talking about u substitution and more definite integration. So finding the area in between curves. Ooh, we might even start orienting our rectangles horizontally instead of vertically. It's going to be great. I hope you have a wonderful weekend. We'll see you.